Welcome to EPG Pathshala. In this module, we shall discuss Slutsky theorems, multivariate CLT, and then pass on to univariate delta theorems. Actually, in our last module, we have seen how probability convergence and distribution convergences are important in large sample theory. And in this module, in Slutsky theorem, we start with their combination of probability convergence and distribution convergence, and then discuss what is known as multivariate central limit theorem. And then we shall also discuss Cramer-Old theorem, which actually relates convergence of multivariate random variables to the convergence of univariate random variables. Then we pass on to delta theorems. Actually, delta theorems are very important in large sample theory. For example, if we have some sequence of random variables with some large sample distribution, and we require the large sample distribution of some function of such a sequence of random variables. So, delta theorems give us a way to find the large sample distribution of a transformation of a sequence of random variables. And then finally, we shall discuss some examples and regarding delta theorems, and lastly we shall show that whenever the delta theorem is not applicable, but we can still find the large sample distribution of some transformation. So, as we have discussed, we shall start with Slutsky theorems. Actually, in our last module we have seen probability convergence and distribution convergence, and Slutsky theorem is a combination of these two modes of convergence. Then we pass on to our next topic, which is about Taylor expansion, where the arguments are the random variables, and then discuss univariate delta theorems. Of course, all these will be supported by adequate examples. So, let us start with Slutsky theorems. Let xn yn be a sequence of random variables, and let a be a constant. Then if xn converges in distribution to x and yn converges in probability to a, then we have xn plus minus yn converging to x plus a in distribution. This is the first one for the Slutsky theorem. The next part relates to the convergence of a product of some product of random variables. Suppose xn converges in distribution to x and yn converges in probability to a, then the product xn yn converges in distribution to ax, provided a is non-zero. However, if a equal to 0, we have the product xn yn converging to 0, but not in distribution, it is in probability. The last one for the Slutsky theorem gives that if xn converges in distribution to x and yn converges in probability to a, then the ratio xn divided by yn converges in distribution to x divided by a, provided a is not equal to 0. Actually, the Slutsky theorem for ratio of random variables comes from the product of from the Slutsky theorem for the product of the random variables. So, let us illustrate with some examples. Consider our first example. Let xn be a sequence of IID random variables with mean mu and variance unity. So, first of all, assume that this mean is non-zero. Now, consider the convergence of square root of n x bar square minus mu square, where x bar is nothing but the sample mean based on n IID observations. Then we can write square root of n multiplied by x bar square minus mu square as square root of n multiplied by x bar minus mu into x bar plus mu. The first term converges in distribution to normal 0 1. This follows from central limit theorem, whereas the second term converges in probability to twice mu. Hence, we can apply Slutsky theorem here, because we have some product of two random variables, the first one converging in distribution and the second one converging in probability. So, combining these two from Slutsky theorem, we find that square root of n multiplied by x bar square minus mu square converges in distribution to 2 mu times in standard normal variables. So, in all we can say that square root of n x bar square minus mu square converges in distribution to normal 0 and with variance 4 mu square. Consider our next example. Suppose xm are IID random variables with mean 0 and variance unity. Then define yn as the sum of squares, that is summation I from 1 to n xi square. Then naturally yn has a chi-square distribution with n degrees of freedom. Since xn square are IID, so here we are using xn square as our observation. So, since xn square are IID with mean 1, it follows from weak law of large number that their average, that is 1 by n summation I from 1 to n xi square converges in probability to 1. So, consider the statistic Zn, which is defined as square root of n multiplied by x bar whole thing divided by the sample variance, that is 1 by n summation I from 1 to n xi minus x bar square. Then we find that the numerator converges in distribution to normal 0 1 and the denominator being the sample variance, it converges in distribution to unity. So, using and which is non-zero. So, using Slutsky theorem we can at once say that Zn converges in distribution to a standard normal variable. Consider our next example, that is example 3. Let xn be a sequence of IID random variables with mean 0 and variance unity. Consider a new random variable wn defined by square root of n summation I from 1 to n xi whole thing divided by summation I from 2 to n xi square. As earlier, xi square are IID with finite mean unity, and therefore it follows from weak law of large number that as n tends to infinity, summation I from 2 to n xi square whole thing divided by n converges in probability to 1, which is non-zero. Again, from Lindeberg-Levy CLT for IID random variables, we at once have square root of n multiplied by x bar converging in distribution to normal 0 1. Therefore, we can write the whole thing as square root of n summation xi by n whole thing divided by summation I from 2 to n xi square divided by n. So, the first term, the numerator converging to a standard normal variable in distribution and the denominator converging to unity in probability, and hence as an easy consequence of Slutsky theorem, we find that the large sample distribution of Wn is standard normal. Consider our next example, which is a bit complicated as compared to the previous ones. Suppose xn are IID random variables with 0 mean and variance unity, and in addition we assume that the fourth order moment is also finite. Now define the new random variable yn as square root of n multiplied by x1 x2 plus x3 x4 plus up to x2n minus 1 up to x2n whole thing divided by summation I from 1 to n xi square. As earlier, xi square are IID with finite mean 1, and hence it follows from weak law of large number that summation xi square divided by n converges to 1 in probability. Now consider new variables zi, which is defined as x to I minus 1 multiplied by x to I, and we find that zi are IID random variables with 0 expectation and variance unity. Actually xi are IID and having mean 0, so expected value of zi is nothing but 0, and as regards the variance of zi, we find that variance of zi is nothing but the product of expectation of x to I minus 1 square multiplied by expectation of x to I square. So each term is unity, and therefore zi are IID random variables with 0 expectation and variance unity. Then from Lindeberg-Levy CLT for IID random variables, we find square root of n z bar is asymptotically normal 0 1. Hence, by Slutsky theorem, we can say that yn converges in distribution to a standard normal variable. Next, we shall discuss multivariate central limit theorem. So far we have discussed central limit theorem for univariate random variables, but often we have random vectors or sequence of random vectors, and as earlier we need to apply central limit theorem or develop central limit theorem for such sequence of random vectors. So we shall discuss one such central limit theorem now. Consider an IID sequence of p component random vectors xn, that is xn are p cross or p component random vectors with expected value mu and a positive definite dispersion matrix sigma. In fact, it is already known that dispersion matrices are always non-negative definite, but to apply multivariate CLT we need a positive definite dispersion matrix sigma. So if x bar, which is again a p component random vector, is the average of n such p component random vectors xn, then square root of n multiplied by xn bar minus mu converges in distribution to a p-variate normal distribution with mean vector 0 and dispersion matrix sigma. So this is just an easy extension of Lindeberg-Levy CLT for univariate IID sequence of random variables. Our next theorem is somehow interesting. This is known as Kramer-Old theorem. For a sequence of random vectors xn converges to x in distribution implies and implied by the scalar product of a and xn converges in distribution to scalar product of a and x, where a is some p dimensional vector. So this actually this result has tremendous importance in large sample theory, as we shall discuss it. So now we start our next topic, which is known as a delta theorem. So consider a sequence of random variables xn such that the large sample distribution of xn is identical with the distribution of x, and where x is some non-degenerate random variable. Suppose we are interested in the large sample distribution of some function gxn. Naturally, if the actual distribution of xn were known, one could use the techniques of sampling distribution to find the exact distribution. However, as indicated earlier, finding the exact sampling distribution is often cumbersome. So it depends on the underlying model, and it depends on the available mathematical techniques. In large sample theory, one can find the large sample distribution of such a function of random variables in a remarkably easy way. The results associated with finding the asymptotic distribution of a function of random variables are known as delta theorem. So we have used Jacobian technique to find the exact sampling distribution of functions of random variables, and now we shall show how asymptotic distribution of a function of random variable can be found using these delta theorems. So let us start with an useful result. Actually, this result is related to Taylor's expansion with random arguments. So the result is like this. Consider a sequence of random variables xn such that xn minus theta converges to 0 in probability if the function gx has d derivatives at the point theta. We have, as n tends to infinity, gxn equal to g theta plus xn minus theta multiplied by first derivative of g theta plus xn minus theta whole square by 2 factorial multiplied by the second derivative of theta up to xn minus theta whole to the power d divided by d factorial multiplied by the dth order derivative of theta plus small op1. So for proof, we consider the Taylor expansion. Now from Taylor expansion of gx around theta, we have the relation that gxn equal to g theta plus xn minus theta multiplied by the first derivative of g theta plus xn minus theta whole square divided by 2 factorial multiplied by second derivative of theta up to xn minus theta whole to the power d divided by d factorial multiplied by dth order derivative of g plus Rn, where Rn is the remainder and Rn tends to 0, whenever xn tends to theta. So it will be sufficient to show that this Rn equal to small op1, that is Rn converges in probability to 0. Now note that the event that modulus of xn minus theta less than epsilon implies absolute value of Rn is less than delta for arbitrary epsilon and delta, and both are positive. Now we have assumed that already that xn converges to theta in probability, and hence we find Rn tends to 0 in probability. Hence the proof concludes. So now we are in a position to describe our delta theorem of first order. This particular result is known as Mann-Wald theorem. Consider a sequence of random variables xn such that square root of n xn minus theta converges in distribution to x. Let g theta be a real valued function such that the first derivative of g theta is continuous and non-zero in a neighborhood of theta. Then square root of n gxn minus g theta converges in distribution to a random variable which is the first derivative of g theta multiplied by x. In particular, if x has a normal 0 sigma square distribution, that is a normal distribution with variance sigma square means 0, then the convergence holds to a normal distribution with mean 0 and variance sigma square multiplied by the first derivative of the square of the first derivative of g theta. So let us discuss the proof of such delta theorem. Assume that g dash x is continuous in the neighborhood absolute in the epsilon neighborhood of theta. As a consequence of the fact that square root of n xn minus theta converges in distribution to x, we have that for every delta greater than 0, probability that distance between xn and theta less than delta is nothing but probability that square root of n multiplied by distance between xn and theta less than delta multiplied by square root of n, which tends to 1, and because of the fact that square root of n xn minus theta converges in distribution to a non-degenerate random variable x, and this immediately gives a fact that xn converges to theta in probability. Then using Taylor expansion, we have the representation square root of n gxn minus g theta equal to square root of n xn minus theta multiplied by g dash theta plus small op1. Since square root of n xn minus theta converges in distribution to x and op1 tends to 0 in probability, it follows from Slutsky theorem that square root of n gxn minus g theta converges in distribution to some random variable which is the first derivative of g theta multiplied by x, and this proves the result. So let us quickly observe some points in this proof. First of all, it is interesting to note that for normally distributed x, the distribution of gx defined, for example, gx may be e to the power x or x square, is not normal. For e to the power x, the distribution is log normal, and for x square it is non-central chi-square or central chi-square. But we find that the large sample distribution of gx is normal whenever the g function g satisfies some conditions. So this is not unusual, as for large n we have approximated gxn by a linear function of xn. Since xn converges to theta in probability, every neighborhood of xn containing theta has probability content unity for large n, and in a small neighborhood a differentiable function is almost linear. And since the linear function of a normal variable is again normal, we find the large sample distribution as normal, and this is just a heuristic justification of asymptotic normality of gxn. So next we shall discuss delta theorem of higher order. Actually, in our last theorem we have assumed that g dash theta is continuous and is non-zero, but in practice depending on the different values, different functions, different choices of g, this g dash theta may be 0. So in such a case delta theorem of first order is not applicable. So we need the higher order delta theorem. So consider a sequence of random variables xn such that square root of n xn minus theta converges in distribution to x. Let g theta be a real valued function such that the derivatives of g theta up to order m minus 1 are all 0, but the mth order derivative of g at theta is non-zero. Then m factorial multiplied by n to the power m by 2 multiplied by gxn minus g theta converges in distribution to x to the power m multiplied by the mth order derivative of g at theta. In particular, if x has a standard normal distribution and m equal to 2, then n times gxn minus g theta converges in distribution to chi square 1 multiplied by the second order derivative of g divided by 2. So, as a proof, we first note that as a consequence of convergence in distribution for the sequence of random variables xn, we have that xn minus theta converges in probability to 0, and since xn converges in probability to theta, we have from Taylor's expansion that gxn minus g theta equal to xn minus theta whole to the power m divided by m factorial multiplied by gm theta, that is the mth order derivative of g theta plus small op 1, or equivalently we have the representation that n to the power m by 2 multiplied by gxn minus g theta equal to square root of n xn minus theta whole to the power m divided by m factorial multiplied by the mth order derivative of g at theta plus op 1. And hence, as earlier using Slutsky theorem, it follows that m factorial multiplied by n to the power m by 2 gxn minus g theta converges in distribution to x to the power m multiplied by the mth order derivative of g theta evaluated at theta. So, we immediately have some observation from this delta theorem of higher order. In most of the cases, x is standard normal, and hence the asymptotic distribution involves the distribution of the mth power of a standard normal variable, which is straightforward. Next observation is that it is interesting to note that gxn better approximates g theta when g dash theta equal to 0, but g double dash theta not equal to 0. In this case, the convergence rate is faster than the previous situation. Actually, the first derivative of g equal to 0 at theta implies that g varies very little in a small neighborhood of theta. Thus, if xn is close to theta, gxn will be very close to g theta, that is in such a case approximation is better. So, let us start with some examples. Suppose xn are binomial 1p variables, then from CLT it follows that square root of n x bar minus p converges in distribution to normal 0 p into 1 minus p, where as usual x bar is the sample mean. Suppose we need to find the asymptotic distribution of an estimator of odds ratio Gp, which is defined as p divided by 1 minus p. Naturally, x bar divided by 1 minus x bar is consistent for Gp. Again, we note that the first derivative of g, which is 1 minus p whole to the power minus 2, is non-zero in neighborhoods of p. Therefore, we can apply delta theorem of first order, and this theorem gives that square root of n x bar divided by 1 minus x bar minus p divided by 1 minus p converges in distribution to a normal variable with mean 0 and variance p divided by 1 minus p whole cube. Let us consider our next example. Suppose xn are IID normal theta 1 variables where theta not equal to 0, and we are interested in g theta equal to theta square. Naturally, a consistent estimator is g x bar equal to x bar square. Now, from the CLT, it follows that as n tends to infinity, square root of n x bar minus theta converges in distribution to a standard normal variable. Since the first derivative of g at theta is not equal to 0, as we have assumed theta not equal to 0, then it follows from delta theorem of first order that square root of n multiplied by x bar square minus theta square converges in distribution to a normal variable with mean 0 and variance 4 theta square. Consider our next example, which is on binomial 1 theta distribution where theta is the success probability belonging to the open interval 0 1. And suppose we are interested in g theta equal to theta multiplied by 1 minus theta, that is variance of xn. Naturally, a consistent estimator is g x bar equal to x bar multiplied by 1 minus x bar. Now, assume that theta not equal to half, so that the first derivative of theta g theta is 1 minus 2 theta, which is not 0. Then by delta theorem of the first order, we have square root of n x bar into 1 minus x bar minus theta into 1 minus theta, converging to a normal distribution with finite variance depending on theta in distribution. However, for theta equal to half, we get g dash theta equal to 0, but the second derivative of g at theta is a constant, that is minus 2. Hence, we have to apply second order delta theorem in order to get the large sample distribution in this case. So, using the second order delta theorem, we find that 2 factorial multiplied by n to the power 2 by 2 into x bar into 1 minus x bar minus 1 by 4, converging in distribution to a random variable which is x square multiplied by second derivative of g at theta, where x has a normal distribution with mean 0 and variance 1 by 4. Thus, we finally get that n times x bar into 1 minus x bar minus 1 by 4 converges in distribution to a random variable which is defined as minus chi square 1 divided by 4. So, we have just seen how delta theorems are important in statistics and what are their pros and cons. We have also seen some examples on first order delta theorems and second order delta theorems, and we find that even if the exact distribution is different from normal, but the large sample distribution for some transformation is always normal, obviously if some conditions are satisfied. So, in our next module, we shall discuss some extensions of delta theorems. Actually, in this module we have discussed delta theorems of first order and second order considering only univariate random variables, but as we have discussed that we have sequence of random vectors. So, in such a case we always have some version of delta theorem, and in our next module we shall discuss those versions of delta theorems and of course give some examples.